In this video, we're going to talk about the perceptron machine learning algorithm. So perceptron is this weird-looking word that comes from the 50s when people came up with the first version of the perceptron, where it's just a very simple classification function that pretty much directly makes its predictions, decides on its output based on its percepts, which I guess is why it was called the perceptron. So the plan for the video is we're going to first go over the basic perceptron, which was formulated to predict binary outputs. So it's going to predict something as either true or false, or we're going to notate it as either +1 or -1, or positive or negative. Then we'll look at a variant of perceptron that is able to output predictions in multiple classes. So it can predict something like whether something is a dog or a cat or a bird or a turtle, where there's many possible labels for an image of an animal, or just like in our homework problems, we're going to see situations where we can label an image of a digit 0 through 9, any of the values between 0 and 9. And that's a little bit more complex than if we're just labeling something as true or false. So perceptron algorithm is also known as a single layer neural network. So a single layer neural network. And the reason it's sometimes called this is because the perceptron's a member of a family of models that are referred to as artificial neural networks. And we've already looked at some networks that we've been using for reasoning or for AI reasoning. So we saw the Bayesian networks, and we saw that Bayesian networks use a network structure to describe dependencies between probabilities, or between variables rather, and their probability distributions. And an artificial neural network does something kind of similar in the sense that it also has this network structure where the connections between nodes represent relationships between or interactions between neurons. So each node is meant to represent an artificial neuron that takes in as a bunch of inputs its parents' values and computes whether it's going to be an activated neuron. So this gets a little bit complicated. We'll talk about these more and the more exotic neural networks. But the perceptron, since it's a single layer neural network, is actually quite simple. And when you look at the picture, you'll recognize this same structure as the naive Bayes structure, but this is going to be a little different than naive Bayes. So what this represents is that this single layer neural network is a linear classifier. So it's going to be a classifier that outputs a prediction based on the sign of a bunch of weights times the input features. Okay, in other words, and the sign is just this simple thing where if it's positive or great or 0, it outputs +1, and if it's negative, it outputs -1. So this gives us some notation to label some of the things in the picture above. So the picture should look like this. So the input nodes are the nodes at the top, the blue nodes, and those are your input features. Those are your measurements that you take from whatever input you have. And the W's are your weights, and the weights essentially represent your model in the same way that our linear weights represented the model for our approximate, Q-learning agent or TD learning agent. So this is the same idea. So we're going to have these linear, or these weights that interact linearly with the input features, and they together attempt to output a Y value, which is your prediction. So that's how prediction happens. That's what happens if somebody gives you the W values, right, the model, and someone gives you an X input, and all the measurements of X1 through X5 in this diagram, then the perceptron does prediction, does its output just by multiplying the weights by the features and summing them up and then seeing if it's positive or negative. Okay, so that's pretty straightforward. Like I said, very simple. What we do next is then we want to say, what do we do if we are given inputs X and true labels Y given to us by an expert labeler, and we don't have W. We want to learn W. We want to figure out what values we should set for W1 through W5. So the algorithm that people have discovered, in I guess has now been 65 years since people discovered it, is one that uses the online learning setting. So if everything goes according to plan, you would have heard about this in class on Monday. So the idea is that in an online learning setting, we're going to get one example at a time, one label at a time, and our job as an online learner is to update our model based on that input without storing that input. So we're not going to store all. We're not going to necessarily store all of our inputs that we've seen so far. So we won't really have a memory, or the only memory of what the things we've seen will be sort of encoded in the W's. So here's how it works, right? We get an example X and an oracle label Y. And as I said, our goal is to then try to update W if we need to. And so this is the basic, I guess, very high level principle behind Perceptron, the Perceptron learning algorithm. So what we do is we try the current classifier. So we compute f of x, and then we compare. Is f of x equal to the true label? And if it is, then we celebrate, right? Then we're happy. We don't have to do anything. However, if f of x is not equal to y, then we're going to have to do something to fix this problem, right? We've gotten the example that we got wrong, so we want to now adjust our model to fix our mistake. So let's look under the hood and try to figure out what we can do formally to fix our mistake. So the prediction function looks like this, right? It's a sign of a linear combination of the input features where the linear coefficients are these w's. There are model parameters. But if you just think about it, you can sort of pop up a level in between, the full low-level view and the high-level view of it just being a function. Inside the sign, there's going to be some number. That number is is that weighted combination. The number is the score. So there's going to be some score inside the sign, and the question is, what are the types of errors we can make? So the first type of error we can make is that the true label is positive, is +1, and our f of x predicted -1, which means that the score ended up being negative. Our score was below 0. And intuitively, right, the correct way to fix that problem is to move w so that it's no longer negative. So w times x is no longer negative. Or in other words, make w times x a little bit bigger because it was too small. And then the other type of error is the other direction, where you have, the true label, the true oracle tells you that y is -1, so it should be negative, and we predict positive, which means that our score function, w times x, was too big. So let's make it smaller. Let's figure out how to make it smaller. Okay, and that's the basic intuition, is that we just want to adjust the score, make it bigger or smaller, depending on what type of error we made. Pretty straightforward. Okay, and then the recipe that people came up with is as follows. I'll just show you the whole thing. So this is the recipe. It's just these two cases. Right, in the first case, you subtract x if you need to make your scores smaller. In the second case, you add x if you need to make your score bigger. And just for completeness, if you are correct, you do nothing. Right, so the last step is just a no operation, a null operation if you're correct. Okay, and we can also further make this more compact by just writing it like by taking advantage of the fact that we've used y to represent either +1 or -1. So we can just write this, and that's the same thing, right? It's just we multiply the label or the sign of the label by our input example, and that's our update. So we can just cross those out. Those are still correct. It's just simpler or more compact to write it as two cases. Okay, so now let's walk through an example of this update and just sort of visualize what it does. So imagine that you have an f of x and you predict +1. And just for the sake of, okay, so one example is that now maybe y is +1, in which case we don't do anything. But let's think about the more interesting case when we make an error. So we make an error because y is actually -1. So we predicted +1. The true label is -1. So what do we want to do? We want to now update by subtracting subtracting x from w. Okay, and let's throw in some numbers just so that there's some concrete numbers. Let's say w 1 is 2, let's say W2 is 1, let's say x1 is 3 and x2 is 1. Okay, so so if we add these up, we get 7, right? So it's positive, it's way too big, right? We wanted something that was below 0, but when we ran our score function, we got 7. It's huge, well, relatively. So let's run our update. So the update now says we're going to update W1 by subtracting x1 from it, and W2 by subtracting x2 from that. And we end up with, minus 2 times 3 plus 0 times 1. And it turns out that in this case, we now get to a situation where, for this example, we would now have predicted correctly, right? We would have predicted minus 6 instead of what was originally 7. But it doesn't always work that way. Sometimes you just improve or you reduce, how far off you were, but you don't necessarily get the right answer. And sometimes you also get situations where you adjust your weights and it actually hurts you because you've over adjusted your weights. Now the good news is that Perceptron is guaranteed to eventually find weights that satisfy all of your data, provided your data is actually able to be separated by a linear classifier, right? So if it's actually possible for if some W to correctly classify all of your data, then if you run through your data enough times, you will eventually get to a setting of W that exactly classifies and correctly classifies all your data. So let's also think about this. Let's think about the question of, why are these operations the right things to do? So again, remember the intuition is that we want to increase the score when we're wrong because we're too low, and decrease the score when we're wrong because we're too great. Our score is too great. And so let's just see if that works out. So let's consider both possibilities of errors we can make, and we'll consider this one first. The first one is where the true value is positive and our prediction was negative. So again, in this setting, which way do we want to adjust W? We want to just adjust W so that we end up with a score that is bigger, that is more positive. It doesn't necessarily become positive, but it should be more positive. So this is the prescribed update, right, from the the prescription, from the recipe, and the question is, right, is this actually going to result in a greater score than the original value? So I don't know. Take a second to think about it, but it's pretty obvious. It does, and one reason you can show that is that you can distribute this product inside the parentheses, and you end up with these two expressions or these two terms. And you can see that now on the left side we have a w times x, and on the right side we have a w times x plus an x times x. And x times x, right? That's always positive, or rather, that's always non-negative, provided that x is, well, it is always positive when x has some non-zero entries. Otherwise, it's 0. So that's great news, right? We've now shown that this recipe step does in fact increase the score of your perceptron on that one example. And then we can go the other direction and just double check this as well, and we get the same kind of thing. And now we're subtracting x times x, which is always positive, which means we're going to always decrease the score. Okay, and let's visualize this. And again, I'm leaving out there's some very beautiful theory that it takes a lot of work to really parse through. So we don't have to worry about it. We can just take it on faith. But the interesting, very exciting theory is that this thing actually converges. This thing actually, even though we're just correcting the score for this one example, it turns out if you keep pulling examples from a distribution or from the real world that can actually be separated by a linear classifier, you will get a correct linear classifier eventually. So let's look at some pictures. All right, so here's a diagram of some training examples. So pretend we have a data set of 6 points. They're meant to be classified as blue circles or green X's. And let's say we start out with some randomly initialized weight vector that gives us this separator Okay, so here's what I'm drawing here. The shapes of each of these points are their true labels, okay? And the colors represent whether we classify them correctly. So if it's blue, that means we correctly classify it as a circle. If it's green, we correctly classify it as an X. And if it's red, that means it's incorrectly classified, right? We got it wrong, right? So you can see, for the current weight vector that we initialized it to, the top left, everything to the top left of the weight vector of the separating line, our f of x predicts it to be a circle, which means that x, right, that x on the bottom left, around 1.4 or 1.41, is incorrectly classified. We think it's a circle; it's actually an x, so it's red. Similarly, on the right, we have a circle at 1.5 that we think our current model is telling us is an x, but it's actually a circle. Okay, so let's visualize what happens when we do learning. So we're going to iterate through each data point. I'm going to circle the data points in green to show which one we're considering right now. And we're going to go through the entire data set a couple times. So each time we go through the data set, it's going to be called an epoch of learning. I guess it's sort of a very dramatic way of describing, how we're just going through the data set more than once. So right now we're in epoch 1. So we're still in the first sweep through all the data, and we're looking at example 1. So example 1's on the top left, and we're happy because it's classified correctly, which means our Perceptron update rule says don't do anything. Okay, let's look at example 2. So this is example 2. Example 2 is classified incorrectly, right? And so what we're going to do is we're going to subtract x from w to adjust w to correct things. So the values of w and x are listed on the bottom, and we're going to do the subtraction, and we end up with this. So this is the totally brand new line, but it does correctly classify that point, I guess, which is good. But what's happened is we've now misclassified a new point that we hadn't previously been misclassifying. So we're going to continue going through the data set. So now we look at this point, the x on the bottom left. It looks good. We're classifying it as an x, and then we get to example 4. So example 4 is this new one that we misclassified, and it's now going the other direction. It's the incorrect label the other way. Right now x, now we think it's an O, but it's actually an x. So this time we're going to actually add x to w because it's the other direction, and we end up with this new weight vector. And looking at this now, this kind of stinks because we previously fixed that that O a couple of rounds ago, but now we're back to getting that one wrong again. But that's okay. We're going to keep going. So the next sample we look at is example 5, and it's classified correctly, so we're fine. And finally we get to example 6, and that one's fine. Okay, so now we're done. We went through the entire data set once. That was epoch 1. Epoch 1 is now over, and basically we didn't actually get anywhere. But we're going to keep going. So in epoch 2, we look at example 1, classified correctly, great. Example 2 is wrong. So now we're going to once again subtract x from w. But this time w has been grown a bit. Originally w was kind of small in magnitude. Now it's bigger in magnitude. So it's when we subtract x, it doesn't get as shifted as much as it did before. And when we do that, when we subtract x, we get a a line that separates all the data correctly now. We can look at it as humans looking at this picture and see that it's correct. But what we're going to do is we're going to actually continue going through the rest of the data until we have seen all the data and have seen that we've gotten all of it correct. Okay, so let's just summarize. So this is the Perceptron learning story. It's all in one slide. So we predict with this f of x, that's just the sign of this dot product, of this linear combination of weights and features. Okay, and then we update with this this simple rule that just says if we're wrong, we add to our weight vector y times x, or we can optionally add a learning rate so we maybe don't jump as much as we did in the visualizations on the previous slide. We could make alpha 0.1, so we're more smoothly moving around the space of possible W's. And another way we can enhance things is we can add a bias term. So this essentially adds the ability to shift your linear combination score up and down without, independently of your input data. And this you can again visualize why this would be useful. On the previous slide, we had this two-dimensional weight vector, and every single separating line had to go through the origin. It had to go through 0, 0. So the B term allows us to shift that. And then we have to add this extra step to update B when we make a mistake. Okay, so that's the whole thing. This is binary perceptron on one slide. If you can even call this a full slide, it's got basically 3 equations on it. So it's pretty straightforward. And now what we want to do is we're going to do something a little bit more complicated for our homework. And for the homework, what we're doing is multi-class output. So what we had seen so far is just a situation where we need to predict positive or negative. And what you could do with that is maybe you could design a classifier that takes as input images of digits and predicts whether they are zeros or ones, which is great. You can do binary prediction. That's great. In practice, right, we usually have situations where we have multiple possible labels or multiple possible classes. It's not just 2 classes. It's not just positive and negative, but it's 0, 1, 2, 3, 4, et cetera, et cetera. So we want to come up with a way to handle this, and there's a few ways to do it. And the way we're going to do it for the homework is one of the good ones. It actually is a nice generalization of perceptron that leads to a further generalization we'll get to later on for doing structured outputs. So, but that's an aside. So let's just talk about multiclass output. So the multiclass perceptron basically does this, and here's the rest. Again, I'll give you the recipe first, and we'll think about it a little bit longer. So the recipe is that we're going to have separate weights for each class. So each of these W's is a vector of weights, of the dimensionality of the input features, right? So if we have 64 input features, then W0 is length 64, W1 is length 64, W2 is length 64, etc. And our prediction is going to then look at the scores for all of these separate weights and output the best scoring class, the best scoring class. So it's going to look like this, right? It's going to be the argmax over the class y prime, where the score that we're argmaxing is is that linear score of the W for that class y prime times the input x. And at this point, we could optionally add in a bias b term, right? Just like in the single or the binary perceptron. But for now, I'm going to leave that off the slide just because it's sort of trivial to add, and we don't use it in the homework. So the learning update then looks a little bit different, but only a little bit. So this is the update, and right again, here's the recipe. Let's think about it now. So what we do is we look at so there's two classes that we're going to consider. Y is the true label, right? We've always been using Y as the true label. So for the true label, or for the weight vector for the true label is going to be updated by adding X. And if you'll remember the sort of the way directions that these things went, when we add X to W, what happens is the score for that example increases for that weight vector. So we're increasing the score for the true value. And then for f of x, for whatever f of x is the class that we predicted this example lives in, for that weight vector, we're going to subtract x, which again, think about the directions, that's going to decrease the score. That's going to make the score lower for the class that we actually chose. So that's a little bit weird because we're in this recipe, we're actually changing things no matter what, right? Even if we get things right. But we'll see that things cancel out nicely so that it works out. So let's go through 2 examples. We'll go through 2 examples. So the first example, we're going to get this as input. This is our input. It's this image of what looks like the character 2. And then the ground truth, the oracle label, is that it is 2. This is exactly 2. All right, and let's say we run our argmax over all the classes using our current weights, and the best scoring class, or the best scoring weight vector, is 6, is the class 6. And I don't know, maybe this could have happened because we built a classifier that's invariant to mirror image flips, right? So if you flip this 2 image left to right, it kind of looks like a 6. I don't know. I'm just being imaginative here, but it doesn't matter. Let's just say that's what happens. Let's just say that you get f of x is 6, meaning that w6 had the highest score. So let's run our 2 updates from the recipe. So the first is we're going to update for the ground truth, the true label 2. So w2, and that's an index 2, not a squared. It's not an exponent. So w2 becomes w2 plus x, which makes w2 times x greater. And then w6 becomes w6 minus x, which makes w6 times x lesser. So that's pretty much what we want, right? Like basically what, think about what happened in this situation. We got an input, it was supposed to be 2, it was supposed to be labeled as 2, and we instead labeled it as 6. And what we wanted was that our score for 2 was actually going to be the argmax. If had it been the argmax, we would have been correct. But instead, 6 was the higher score, or W6 gave a higher score. So what we've done here with this update is we've made W6 times X, that score, lower. We made the wrong score lower, the one that we got wrong, lower. And we made the correct score that we wish we had gotten higher. So it's very, very intuitive, at least in that context. Once you think about the vector geometry, it becomes a little bit less intuitive, but it still works out. Okay, and then the second example I want to consider is what happens if we get the correct label. So, and this is really quick. So we output f of x equals 2, which means that w2 times x was our highest scoring linear combination. And let's just run the updates. So the first thing again is we're gonna update the weights for the true class for y, which in this case is 2. So we make the score a little bit bigger, or we make it bigger for w2, and then the second thing we do is we're going to run the update for f of x, what we predicted, and we make the score for w2 times x a little bit smaller. And if you run these updates in sequence, you can combine them and just write them as this, which just becomes that. Right? It's a no-op at this point, which is what we want. And so you could when you go to implement this, you could just check if you did it correctly and just do nothing if you labeled things correctly, or you could not check and just run these updates blindly. It's probably not going to make much of a difference for these homework problems, but in practice, if let's say if your feature dimension space is really huge, you could save some time by not running this update at all when you're correct. Okay, so let's summarize. We're almost done. So the perceptron is a linear classifier that multiplies weights by input features. So that's the whole, sort of output procedure at test time. At learning time, what we do is we learn by updating when we're wrong. So it's an online algorithm, which means we're going to get one example and one label at a time, and we're going to try out our current classifier, and if we're wrong, we're going to update. And if our score is too low, then we make the score higher. If the score is too high, we make the score lower. And of course, the math is a little bit more nuanced than that, but it's not, not too much more nuanced. And this is just the right way to think about it. Think about what the math is doing. I don't want you guys to just memorize the mathematical formulas. I want you to be able to think about what is it that these formulas are doing. Okay, and then the variant we talked about is the multi-class perceptron, which uses multiple weight vectors. And the idea is you predict by choosing the max scoring class according to its weight vector. And the learning procedure is kind of similar, but it's a little bit different, and the idea is you're going to learn by adjusting the score of the predicted class and the true class. And basically what you want to do is you want to make the true class score higher and the predicted class score lower. And if they're the same class, then nothing happens. Okay, so hopefully that should get you started. You should have sufficient background to certainly get started on the homework at this point. Which is technically not out until Wednesday, but it's on the website now, so feel free to have a look at it.